السلايدات على اعتبار إنه you guys had paying attention in the class, you took notes, but the content within the slide definitely is enough. So no need to study from textbook. انتوا بتشوفوا الأسئلة فين؟ هنا في الشات. Okay. Any other question؟ طب في حاجة مش فاهمينها معينة ولا so
رغم اشوف انا في الجروب العام في كذا شخص يسال عن اشياء، فما ادري ليش احد يسال الحين.
how many we have? 15. Okay. So طيب الناس اللي حضرت ديت يعني what is your wish or يعني when you attended you were looking for what? If you don't have questions.
Doctor, I have a question.
Mm-hmm.
When we're talking about the salt dome, does it have a positive, a negative or non-magnetic anomaly?
So it depends on the surrounding. So if it is surrounded by sedimentary rocks, you wouldn't have any anomaly, because the word anomaly depends on relative differences. So if you imagine a salt dome, low magnetic susceptibility, surrounded by sedimentary rocks and also with low magnetic susceptibility, so at the end you don't have any contrast, so you will not have any anomaly. But if the salt dome is, or the salt formation is associated with some thinning on the basement, this one refers to the igneous metamorphic rocks that have higher magnetic susceptibility. So if that salt dome is forming within a basin and that basin corresponds to a thinning within the basement, then yes, it will be negative in this case. So if that's the scenario, so it depends on really the scenario. It's not like kind of as straightforward as the density in this specific case. Density, it will be negative. Does that answer your question?
Yes, thank you so much.
You're welcome. Any other questions? Any other wishes?
Also, I have another question. I'm sorry.
Yes, go ahead.
How can we draw the magnetic survey graph? Like, what does it depend on exactly? I know that the gravity depends on the difference in the density, but what about the magnetic?
So magnetic surveying depends on the magnetic susceptibility contrast. So some rocks will have higher magnetic susceptibility, like igneous rocks. Some will have low, like sedimentary rocks. Now, if your question how to draw the anomaly, we will never ask you to draw an anomaly, because it's a bit more complex, especially with magnetic, because the shape of the profile will depend really on the latitude and many other things, and the interference between the rock magnetization and the earth magnetic field. So we'll never ask you really about drawing the magnetic anomaly. But what we want is an insight about really, is it going to be high or low, things like that, relatively speaking, but not to draw.
Okay, thanks.
I have
Okay,
a question.
Yes, go ahead.
في السلايدات موجود إن one of the reasons why gravity isn't constant is because the ellipsoidal shape which affects the radius.
Yeah.
وفي lecture ثاني موجود إن ellipsoidal shape affects gravitational force. So does the ellipsoidal shape affect both gravitational force and radius, or what?
Oh, sure, yeah. So it impacts the gravitational force because it impacts the radius. And the impact of the radius is two things. So first is in the equation Probably we can pull out. I think I can share my screen. I think. I hope. Let me see if I can share now my screen. Yes, can you guys see my screen? Yes? No? Okay. So what happens is that this is the radius. So the radius will impact F, which will impact, of course, over here maybe. So this little g is going to be impacted by the radius. So that's the first impact. But also, as we mentioned before, remember this is F. It's kind of the net force, and the net force will be impacted by the relationship between the centrifugal outward force and the internal or the pull due to the gravity. So the impact of the R or the radius is in two things. In the gravitational force, this is the, if you wish, this is the one in red, and the centrifugal force, again, this is R, the radius, which is actually the black. So this is how it really impacts the measurement in this case, because it impacts both the red and the black arrows here. And the net is actually what is shown here in this dark blue. And so it's really twofold. One is impacting the centrifugal force, and one is impacting the gravitational force. Okay? Does that make it clear?
Yeah, makes sense.
Okay. Any other questions? Or any other wishes? Those who already joined this meeting, I'm sure you joined it for a reason. So if you don't have a question, what else you were looking for? Well, that was the agreement with the CBG club, but I'm not sure. It seems some had another wishes, maybe. I mean, there is no time to go over the whole material, but I don't know if you want to go over some of the highlights or the main topics you need maybe to think about or to study.
دكتور أنا أخذت جيوفيزيكس في الترام الماضية، وكان في جزء في أتذكر في المترم جاء إن سؤال كذا في calculations، فأتوقع يعني هذه فكرة حلوة إنه ممكن إذا تقدر تشرحها لهم يعني كإكزامبل آخر ولا حاجة.
أي example. So, I mean, for the calculations, yeah.
هذا البلك مودولوس والأشياء هذه أتذكر جاء عليها سؤالين حتى وأشياء زي كذا.
You're talking about the final, not the midterm. Bulk modulus.
لا في بالميدترم جاء معادلة ناسيها صراحة، أنا جيولوجيست فما أعرف الجيوفيزيكس.
Okay. Anyway, so yeah, when it comes to the calculations, this is one equation you need to know. Yes, you already had a question about it in the quiz. You also had the equation about the bulk density. This is a famous one. You could also expect maybe a question about it. You had already a question about it in the homework. So it's this equation here. Yeah. So this is the mineral or grain density. This is the bulk. This is porosity, all in fraction for the porosity. So yeah, if anyone had a specific question about this, then yes. But these are two equations. Then other equations that you need to also know, and all of these will be given. You don't have to memorize, but you just need to understand. For magnetic, there is really nothing. For electrical, there is one, which is the which one? Which is this one, linking resistance and resistivity. You need to kind of understand and the difference between them. That's it for resistivity. And for GPR is the reflection coefficient, which is this one here, this equation. So these are really the equations, and they will be given to you. So doesn't mean you will have calculations from all, but maybe concept related. But yes, definitely you need to bring your calculator with you, and yeah, make sure you understand how to use these equations, or what do they conceptually also mean. If you have a specific question about something of these, let me know.
Doctor, can you please re-explain the equation for the porosity, the one that you showed it in the presentation?
This one here?
Yes.
Sure. So this is the bulk density. Well, maybe we can do we have the now I am on my screen. I'm not sure if I can really draw. But anyway, so okay, let's go here. So let me see if oops. Yes. So this is the bulk density, and you know, bulk density is the famous equation that, of course, is mass over volume, and it's equal to this guy here. Now, this is the bulk, which is a kind of, if you wish, the total density of a rock is equal to the grain or mineral density multiplied by its fraction in the rock, and its fraction is 1 minus porosity. Yeah, so porosity has to be, in this case, in fraction, not in percentage. So if porosity is 0.1, then it's 1 minus 0.1. This is 0.9. You multiply it by the mineral density in this specific case, and you add to it the fluid density multiplied by the porosity. Again, porosity is going to be in fraction. So if you do that, then you will get your bulk density, and the unit could be gram per cc, or it can be kilogram per meter cube. Yeah, either way. Either ones will, of course, going from one to the other, you will have to do unit conversion. But yeah, so if you don't know how to use the equation, well, let's just use it for an example. So let's assume we have a rock with 10% porosity. So this is porosity. Let's assume the fluid density is equal to 1. And let's assume it's calcite. The rock is made out of calcite. So if it is made out of calcite, then we know that the grain density is going to be around 2.7 as per the table. And again, we will be giving this to you if we ask to find the bulk, and then we need to give you the grain density. So this is gram per cc. So now if the question is to find the bulk density of that rock, then, well, the bulk density is going to be equal to, well, we have it here, so let's do it here. So this one here will be 2.7. So instead of this one, you're going to write 2.7. This is the mineral density, this one. And then multiply by 1, which is the fluid density, multiplied by porosity, which is 0.1. And if you just do the math, then it will be equal to 0.9, which is 1 minus 0.1, multiplied by 2.7, plus, in this case, is going to be 0.1. Yes. And then we just we do the calculation, and we find the answer in gram per cc. Why is gram per cc? Because our input here was in gram per cc. Yes, for both of these two guys. All right. Any question about that?
No, thank you. It was clear.
So this is for the bulk density, which is this one. You need to know what in the quiz or the exams, we will not tell you which is which. So you need to know what is the fluid density, what is the mineral or grain density, and which one is the bulk. Any other question? Well, I think then if no more questions, I will just give highlights of the most important things, probably in And I will do that for the resistivity and the GPR because we didn't have a quiz on these. Now the quiz for gravity and magnetic should tell you what are the most important things in these two chapters. So I think that's covered by the quizzes already, but we'll do it for resistivity in this specific case. Well, for resistivity, you need to know that is an active method where we send a current, and you need to know the resistance and the resistivity, the difference between them. So this kind of slide could be important. Yeah, so we said this equation. So resistance and resistivity. And then you don't have to memorize these, but you need to have an insight about differences. For example, that the salt water is going to be more conductive, which means less resistive compared to fresh water or ice. And that tight rocks in general will have high resistivity and low conductivity because there is very little porosity that will have fluids inside. And then maybe shales and clays will have lower resistivity due to maybe some bounded water and some iron within the minerals. So just in a relative sense, but no need to memorize values at all in this case. Stop me if you have any questions. You don't have to worry about derivation of this one really. Basic layout, it's gonna always be consist of 4 electrodes, minimum 2 to inject the current and 2 to measure the potential difference. Yeah. Well, the different names, yeah, probably you could also have an insight about the different names. Different names is due to some differences in the geometry between them. So that's also something you could know. You need to know what is the difference
Doctor, I have a
between.
question.
Yes, go ahead.
Can you go back? What's the difference between the winner array and the one below it? Because they are same. The delta A is the same for both of them. But what is O exactly? The one located in the center.
Oh, so in that case, you would have an extra kind of electrode. Yeah. So only have 4, except with this one, you'll have a 4th one. So when you measure the potential difference, you would measure it MO and ON. You see that? So well, and also you could measure MN as well if you wish. So in this case, this one here has an extra electrode compared, for example, to the winner. Does that make it clear?
So there is an extra electrode?
Yes. Here, for example, you can have an electrode.
Okay.
So
Thank
in
you.
principle, you could measure the potential difference between M and N, between N and O, or between O and M. While here you could only do it M and N. Okay. Is that clear?
Yes, it's clear.
Stop me if you have questions throughout. Now, 1D profiling is actually where we, this is the 1D horizontal profiling, where we just get an anomaly that is an indication of lateral variability of resistivity. And again, I'm not explaining it. I'm just going over the most important things for you to know. If you struggle to or you don't understand, stop me. Now, in the 1D vertical electrical sounding, essentially what we do, we fix the center point. We just change the spacing to go deeper and deeper. And in this case, this will give me an indication of how the resistivity varies vertically. So that's the main difference with the 1D horizontal sounding. Well, 2D, we just actually repeat the 1D profiling, both for horizontal and vertical, and for that we get a 2D image of subsurface. For application, well, there is not any specific thing you need to know except the fact you need to understand as high resistivity means low conductivity, and that could be analyzed in different aspects. So for a fault, you would be able to image a fault using resistivity if the fault is associated with maybe some of the water that goes from the top at a deeper depth. So if you have a tight rock, very resistive, but then due to the fault, you got some damage zone where the fluid could go from the top and penetrate deeper. And in this case, you see the signal really of the fault. So if the fault is associated with a conductivity or resistivity contrast, in this case, you would be able to use resistivity to map faults. Now, are we going to always have a conductivity contrast with faulting? Not necessarily, but yeah. Now, remember also in this course, we're covering surface electrical methods. And in that case, we cannot go really deeper than, like it's usually shallow application, 100 meter or even less, depending on the spacing of electrodes, but it's for shallow application. Of course, there are other applications that are more straightforward, like seawater intrusion. And when we say intrusion, it means how far the seawater can invade into the shoreline. So we can do that, so we can monitor with time. So we can repeat the experiment. And then we see, for example, the blue here is going to be an indication of the seawater, because the blue is the low resistivity. So that's really more seawater moving or retracting from the shoreline, depending on the time of the year. Of course, more straightforward application is groundwater table determination, things like that. Yeah.
Doctor,
Yes.
there is
Yes.
questions in the comments.
Okay.
You can read it.
You can read it.
Yes.
I didn't understand the difference between rock magnetism and. Okay, let me finish resistivity and then we'll go about it. Okay. Of course, depending on the void, if the void is filled with water or is filled with air, and it depends depending on the surrounding, you could have a positive or negative. The word negative means, of course, lower than surrounding. So if you have a void, the void is surrounded by water. If that void has water inside, then it will be higher conductivity compared to the surrounding. If the void is filled with air, like a tank that is protected from the groundwater, it has air, then of course it will be more resistive compared to the surrounding. Someone is raising the hand. Is that the same thing? Same question in the comment, or this is different? Just unmute yourself and talk if you have a question. Okay. These are just some of the advantages. Now, of course, it cannot work if you have extremely extremely resistive or extremely low resistivity surface. If it is low resistivity, extremely conductive, it means it can short circuit the current, which means the current will not go deeper. And if it is extremely resistant, it means it cannot actually, the current that you inject cannot penetrate the subsurface because it's extremely resistant. So these are some of the limitations of electrical method that you need to be aware of. Yeah, and in general, you need to be able to choose the appropriate method for the appropriate application, depending, of course, on the application. Yeah. So, but this one is for shallow application where we are after contrast in conductivity, like pollutions. If you have oil pollutions near surface, then it could be good because oil will replace water. Oil is more resistive, for example. Yeah. Yeah, so I think that's all. Any question? Now we can go to any question in the electrical. So I hope at least, so you need to know a little bit about application and some terminology as well. Okay. Let me now see the question. So I was asking, I didn't understand the difference between rock magnetism and permanent rock magnetism very well. So the rock magnetism will happen as they are more or less the same. we say that the rock magnetism is permanent, which means it's something that will not change with time. So what happens is during the formation of the rock, and as the rock is cooling down below the Curie point, which means when the rock is cooling below the Curie point, we will have crystallization of the rock. Now the rock will have, especially we're talking about a rock that has some magnetic susceptibility, which means the atoms on that rock will actually align with the Earth's magnetic field during the time of formation. So during the time of formation, there was a specific intensity and a specific direction for the Earth magnetic field. When the rock is cooling down, so it's like magma, let's say, or it's cooling down below the Curie point, then what happens is that alignment can be preserved. So the rock internal structure and atoms will align with the Earth magnetic field at the time of formation. And as it's actually cooling down, as I said, it will crystallize. And when it crystallizes, that magnetism will be locked. When we say locked, it means it will be permanent. It will be preserved. And if the Earth magnetic field changes later on in terms of magnitude or in terms of direction, you know, there is the reversal of polarity. So the north can be south and the south can be north for the magnetic field. The mechanism of the reversal is not extremely clear, but that's beyond the focus of the class. But when that reversal will happen, as long as the rock remains below the Curie point, remain crystallized, remain solid, we will have that permanent magnetization that was locked during the time of formation. We will have it as permanent, which means it will not change. Which means some rocks will have a permanent rock magnetization that is different from the current day Earth magnetic field. So like Earth magnetic, let's see if I can draw something here. Why cannot? Need to be able to draw. Okay, so let's assume during the formation of a specific body, this was the body in the subsurface, the Earth magnetic field was this way. This was like millions of years ago, and this body cooled down below the Curie point, so it will preserve the north. It will align with the Earth magnetic field at that specific latitude. Now, we call it permanent because even changes, like let's assume the Earth magnetic field is being reversed. So the north is becoming now a south. So now now it's pointing this way. So if you come and record now, you are not going to see this one. You will see this Earth magnetic field interfering with the permanent rock magnetization, which is different in magnitude and direction compared to the current Earth magnetic field. That's why we call it actually a permanent rock magnetization, because it can be different compared to the current Earth magnetic field. And actually, this preservation of permanent rock magnetization is the main reason how people could do some aging and a certain understanding about what we call paleomagnetism. Paleomagnetism means what was the Earth magnetic field directions at the time of formations. Probably if you guys have taken already the geology 101 or 102, I don't remember the code, maybe you talked about this reversal of magnetism, which can be observed in mid-oceanic ridges. But what you really need to know in this course, nothing really about the reversal of the mid-oceanic ridges, but rather the fact that rocks can have permanent magnetization if they are crystalline, or if they are cooling down below the Curie point. They will have a permanent magnetization, which means as long as the rock remains below the Curie point, it will have the same magnetization at the time of formation, which could be different compared to what is the current day Earth magnetic field. Now, if we heat the rock above the Curie point again, we destroy that permanent magnetization. So it's only permanent as long as we are below the Curie point. Does that answer your question? Whoever asked the question. Is this clear now? Is there anything still pending? Saba. Okay, I assume. اسكت علامة الرضا. Okay. Any other questions? Okay. Shall I proceed with the GPR? Now in GPR, well, you need to know what does GPR stand for, and you need to know that we are dealing with electromagnetic waves or pulse. There is a source and receivers. We send away an EM wave and then we receive it back. So it's an active method again. We just plot these amplitudes when they arrive, which indicate the contrast in dielectric constant as a function of time. So that's really what we record. You need to know definitely this equation. You don't have to memorize. So essentially what we really, how we can detect object, and this is again another shallow or near surface tool, is the contrast in the dielectric constant. This is really what we are after. And this equation is telling us the reflection coefficient. So you need to know what is the reflection coefficient. You don't have to memorize these numbers, but you need to have a relative sense. So you need to know that metals, so clays, they have higher values, for example, of the dielectric constant compared to, for example, ice, concrete, air, all of these things. And of course, water comes next after metals. And yeah, so just the relative sense is important here, right? Some of the applications is to detect maybe buried pipes, anything that has different electric constant compared to surrounding, as well as being able to see some of these beddings inside the sand dunes or inside geological material. You could see this internal bedding or lamination. This is also another example for GPR, right? Yeah, and of course the as well the frequency. It has a band of frequency, usually from the mega to the gigahertz, and due to that we can only see. Of course, the higher the frequency, the better the resolution, which means we can see smaller object, but the depth of penetration or how deep we can image or look become less when the frequency is higher. So yeah, so that's all I think for GPR. Yeah. In principle, yes. Any other questions? Okay. If no more questions, then I would assume that's it. Wish you all the best. Make sure you come on time. You bring your calculator with you. And بالتوفيق إن شاء الله. Right. Any other questions before we close? Going once, twice. Right. All the best. Where is from CBG Club?
يعطيك العافية دكتور. نهاية
الله
موجود.
يعافيك. Okay, I think that's it then. So we can stop the recording and then that's it. Right. Assalamu alaikum.